So, problem number 10 is, in a system of weakly interacting particles, in equilibrium at temperature T Kelvin, each particle has access to two states with energy difference epsilon 2 minus epsilon 1 equals to 0.1 electron volt. At what temperature will 1/3 of particles be found to have energy energy epsilon 2. This is the first problem, and second problem is rework the above problem by considering the epsilon 2 state is doubly degenerate. So, problem number 10 states, in a system of weakly interacting particles in equilibrium at temperature T Kelvin, each particle has access to two states with energy difference epsilon 2 minus epsilon 1 equals to 0.1 electron volt. At what temperature will 1/3 of particles be found to have energy epsilon 2? This is the first problem, and the second problem is we need to rework the above problem by considering epsilon 2 state is doubly degenerate. So, for the problem number 1, the states are non-degenerate. Okay. So, how we will do that? So, we know N2 by N1 equals to e to the minus beta epsilon 2 minus epsilon 1, where N2, where N1 first, N1 is the number of particles in the energy state epsilon 1, and N2 is the number of particles in the energy state epsilon 2. Suppose capital N is the total number of particles. Thus, N1 plus N2 equals to N. Now, we need to calculate the temperature at which one-third of particles, one-third of total number of particles be found to have energy epsilon 2. So, total number of particles is N here. So, one-third of particles N is the number of particles in the energy state epsilon 2 equals to N by 3, and this is nothing but N2, right. So, the number of particles in the energy state epsilon 1 is 2n by 3, and this is nothing but n1. So, value of n2 is n by 3 and value of n1 is 2n by 3. Thus, n2 by n1 equals to n by 3 by 2n by 3. Okay, so, it gives us half. So, n2 by n1 is half. So, we can write half equals to e to the minus beta epsilon 2 minus epsilon 1, or we can write minus ln 2 equals to minus of beta epsilon 2 minus epsilon 1. So, we get beta is ln 2 by epsilon 2 minus epsilon 1, and the value of beta is 1 by kBt. So, 1 by kBt is ln 2 by epsilon 2 minus epsilon 1. So, the value of temperature T is epsilon 2 minus epsilon 1 by kB ln 2. Now, if we substitute the value of epsilon 2 minus epsilon 1, which is 0.1 electron volt, and if we convert electron volt into a joule, we get, we have to multiply 0.1 or electron volt into, if we convert electron volt into joule, we get this factor. The factor is 1.6 times 10 to the minus 19 joule 1 electron volt. So, 1 electron volt is 1.6 times 10 to the minus 19 joule. Okay. So, kB is 1.38 times 10 to the minus 23 in joule unit, and then value of ln 2. So, if we carry out the, if we further proceed, we get the temperature is 1672.69 Kelvin. So, this is the temperature at which one-third of particles will be present in energy state epsilon 2. This is the first part. Now, second part is we need to rework this problem by considering the degeneracy of the excited state is 2. So, we have when the excited state is doubly degenerate, then you can write n1 by n or n2 by n1 is G2 by G1 e to the minus beta epsilon 2 minus epsilon 1, where G2 rather first G1 is the degeneracy of the energy state epsilon 1, and the value of G1 is 1. So, the state epsilon 1 is non-degenerate, and G2 is the degeneracy of the energy state epsilon 2, and since the epsilon 2 state is energy state is doubly degenerate, so G2 is 2. So, and we know N2 by N1 is half, so half equals to 2 times e to the minus beta epsilon 2 minus epsilon 1. And if we simplify this one further, we get minus ln 2 equals to ln 2 minus beta epsilon 2 minus epsilon 1, okay, and then we get beta is 2 ln 2 by epsilon 2 minus epsilon 1. Now, if we compare this expression with the one we derived before, okay, so we can see that there is one extra 2 term in the numerator. Okay. So, we get temperature, or rather 1 by kBT, beta is 1 by kBT. So, 1 by kBT is 2 ln 2 by epsilon 2 minus epsilon 1. Okay. And then we get T, and the value of T is epsilon 2 by epsilon 2 minus epsilon 1 by 2 times kB ln 2. So, there is extra 2 term in the denominator as compared to the previous one. So, temperature is just half of the previous one. So, 1672.69 by 2 Kelvin. So, it gives us the value of temperature is 836.35 Kelvin. So, when the excited state is when the degeneracy of the excited state is 2, we required half of the temperature when compared to the non-degenerate case. So, this was problem number 10. Next, we consider another very interesting problem based on orthopara hydrogen that we discussed in the class or in the previous lecture. So, problem number 11 says molecular hydrogen is usually found in 2 forms, namely orthohydrogen and parahydrogen. That we know. Molecular hydrogen is usually found in 2 forms, namely orthohydrogen and parahydrogen. Now, the problem, after reaching equilibrium, at sufficiently high temperature or at high temperature, what fraction of molecular hydrogen is parahydrogen. Assuming that each variety or each type or variety of hydrogen is mostly in its lowest energy state. And the next problem is at low temperatures, orthohydrogen converts mostly to parahydrogen explain why the energy released by each converting molecule is much larger than the energy change due to the nuclear spin flip. This is a very conceptual problem, and it states molecular hydrogen is usually found in two forms, namely orthohydrogen and parahydrogen. After reaching equilibrium at high temperature, what fraction of molecular hydrogen is parahydrogen? This is the first problem, assuming that each variety of hydrogen is mostly in its lowest energy state. And the next problem is at low temperatures, orthohydrogen converts mostly to parahydrogen. Explain why the energy released by each converting molecule is much larger than the energy change due to the nuclear spin flip. Now the solution. So Q para is the partition function of parahydrogen. And the different rotational states varies like 0 to 4, like even numbers. And this is the degeneracy factor, and then 2j plus 1 is the degeneracy factor, and then the rotational energy e to the minus j times j plus 1 times theta rotational by temperature. So this is the partition function for parahydrogen. and partition function for orthohydrogen. So, this is the partition function for parahydrogen or molecular partition function. Molecular partition function for parahydrogen. And molecular partition function for orthohydrogen, if we say that quantity is Q ortho, so Q ortho is sum over J goes from 1, 3, 5 all odd numbers of J values, and then 2J plus 1 e to the minus J times J plus 1 theta rotational by T. And Q rotational, as I said, this is molecular partition function for orthohydrogen. And Q para is the molecular partition function for parahydrogen. And theta rotational is the rotational temperature is h to the 2 by 8 pi to the 2 I and then Kb, where h is Planck's constant and I is the moment of inertia of the molecule and Kb is the Boltzmann constant. For high temperature, Q para equals to Q ortho. If that is so, then in para number of hydrogen molecule or number of parahydrogen molecule by number of orthohydrogen molecule is 1 by 4. Now, according to the condition given, in the problem, if temperature is not too high, only states L or J equals to J equals to 0 and 1 exists. Okay. The fraction of parahydrogen is so we say in para by NH2, the total number of hydrogen molecule is Z para by Z and Z or ZH2, where ZH2 is S times 2S plus 1 times so Z para plus S plus 1 times 2S plus 1 Z ortho. Okay. So, N para by NH2 equals to Z para by ZH2 equals to 1 by 3 e to the 1 plus 1 by 1 plus 3 e to the minus twice theta rotational by T. So, this is the answer. Now, the second part B. When T is much lower than theta rotational, orthohydrogen changes into parahydrogen. The energy corresponding to the change in nuclear spin orientation or spin orientation is the coupling energy of the magnetic dipoles of the nuclei and the electrons. So, delta E equals to 10 to the 8 Hertz. Okay. Since the rotational states are related to the nuclear spin state, the rotational states change too also change. The corresponding energy change being, you say that is delta here is h to the 2 by 8 pi square I, and it gives us around 10 to the 11 Hertz. When orthohydrogen converts to parahydrogen, the total energy change is delta E equals to delta ER plus delta ESI, and then this is nothing but delta ER. Thus, the released energy is much greater than delta E. Yes. Or is you can not SI, you can consider SJ. So delta E SJ. Thus the released energy is much greater than delta E SJ. Okay. Okay, so this second part of the problem is a bit conceptual. It's a little bit in tougher side. Okay, but problem A was discussed in the class or in the lecture itself. So this was problem number 11. Next we consider another very simple problem but very interesting one, problem 12. Consider a single magnetic dipole in equilibrium with a heat bath. It has 2 microstates, namely upspin and downspin, having energies minus mH and plus mH respectively. What is the average energy of the dipole? So, problem number 12 states, consider a single magnetic dipole in equilibrium with a heat bath. It has 2 microstates, namely upspin and downspin, having energies minus mH and plus mH respectively. What is the average energy of the dipole? So, partition function Q is sum over I goes from 1 to 2 e to the minus beta epsilon I. So, we get Q is e to the minus beta epsilon 1 plus e to the minus beta epsilon 2, and epsilon 1 is minus mH and epsilon 2 is plus mH. Okay, so, we get Q is e to the beta mH plus e to the minus beta mH. So, this is the partition function and we need to calculate the average energy. So, we know how to calculate average energy once we know the partition function. So, average energy epsilon average is minus del ln Q by del beta, keeping volume constant. Okay. And we have the value of Q here. So, we need to take log first, log of Q, and then we need to differentiate the log of Q with respect to beta, then we will get average energy. Okay. Okay, so, we have Q equals to e to the beta mH plus e to the minus beta mH. So, ln Q is ln e to the beta beta mH plus e to the minus beta mH. Now, if we differentiate ln Q with respect to beta at constant V, we get So, we get average energy epsilon average is minus del ln q by del beta at constant volume. So, we get average energy is mh e to the minus beta mh minus mh if we take out, and then we get e to the beta mh by e to the beta mh plus e to the minus beta mh, or you can write this one is plus minus and this is plus. So, this is the expression for, or this is the average energy value that we wanted to calculate. Okay, so this was problem number 12, and then we can calculate another one problem. Okay, so next problem is based on Fermi energy, problem number 13. It says the Fermi energy in silver is 5.51 electron volt, and the first problem is what is the average energy of free electrons in silver at 0 Kelvin temperature. So, this is the first problem, and the second problem is at what temperature a classical free particle for example, an ideal gas molecule will have this kinetic energy. This means 1.5.1, this kinetic energy. So, problem number 13 is the Fermi energy in silver is 5.51 electron volt. Now, the first problem is what is the average energy of free electrons in silver at 0 Kelvin temperature, and the second problem is at what temperature a classical free particle, for example, an ideal gas molecule, will have this kinetic energy. Now, the solution. First, we consider the problem number 1. So, at 0 Kelvin temperature, the average energy of an electron in an electron gas is given by so we know the value of Fermi energy. Now it's very simple. So if we substitute the value of Fermi energy here, we get the value of E naught 0 is 3.306 electron volt. So the first problem is pretty easy. The second problem. So the solution of the second problem is the kinetic energy of a classical particle at T Kelvin temperature is 3/2 kBt. That we know, we already discussed. Therefore, 3/2 kBt equals to 3/5 times EF, right. So, you get T is 2/5 times EF by kB. So, you get T is 2/5, the value of EF is 5.51 in electron volt. So, if we convert it into joule, we need to multiply this one with 1.6 times 10 to the minus 9 in joule unit, and the value of kB is 1.38 times 10 to the minus 23 joule. Okay, so, we get joule per Kelvin. Okay, so, we get T is 2.555 times 10 to the 4 Kelvin temperature. Second problem is also very interesting, but you need to work out a little bit. Okay. Third or problem number 14. You are, first part, you are given a system of two identical particles which may occupy any of the three energy levels En equals to n epsilon, where n equals to 0, 1, 2, like this. The lowest energy state and if we say that one is epsilon naught is 0 is W degenerate. The system is in thermal equilibrium at temperature T Kelvin. For each of the following cases, determine the partition function and the energy and carefully enumerate the configurations. Case 1 is the particles obey Fermi statistics. Second case is the particles obey both statistics. And third case is the distinguishable or the now distinguishable particles obey Boltzmann statistics. And problem B is discuss the conditions under which fermions or bosons may be treated as Boltzmann particles. Okay, so now the solution. So part A, considering the systems as a canonical ensemble the partition function is, or you just write considering canonical ensemble, the partition function is Q sum over n Gn e to the minus beta epsilon n, where Gn is the degeneracy of the energy level n. Okay. Now these are the distributions when n equals to 0. We have three energy levels, n equals to 0, n equals to 1 and n equals to 2. So both particles can be present in n equals to 0, this is 1 and this is 2, okay, and this is there are double degeneracy there. So you can write like this 0 1, oops, one particle here, one particle there. This is also degenerate, so we can write one particle there. So one particle here, another there, and then one particle here, one particle there. So the value of energy for this case is 0, for this case is epsilon, for this case epsilon, this is 2 epsilon, again 2 epsilon, this is 3 epsilon. Okay. So Q is 1 e to the minus beta times 0 plus 2 e to the minus beta epsilon plus 2 e to the minus 2 beta epsilon plus e to the minus 3 beta epsilon. So, value of q is e to the minus e to the not 1 plus 2 e to the minus beta epsilon plus 2 e to the minus 2 beta epsilon plus e to the minus 3 beta epsilon. So, once we get the partition function, we can calculate energy, average energy. So, average energy E epsilon average is minus del ln q by del beta. Okay. So, if we do it, we get epsilon average is epsilon by q e to the minus beta epsilon times 2 plus 4 to the minus beta epsilon plus 3 to the minus 2 beta epsilon. So, this is the problem when the particles obey Fermi statistics. Okay. So, this is when problem 1, when particles obey Fermi statistics, because when Fermi statistics are obeyed, when the particles obey Fermi statistics, so it says Fermi statistics itself says that no two particles can be found in Fermi statistics, no two particles can be found in one given state. That is why we get this kind of distribution. And for next problem, if we consider the particles are when particles are following Bose statistics. So, in Bose statistics, particles are indistinguishable, but there is no restriction in number of particles in a given state. So, we get the distributions like so two particles can be present here, here, or two particles can be present here, or two particles can be present here. Then one particle here, one particle there, and then so this is n equals to 0 like before, n equals to 1, n equals to 2. So, we get q equals to, so the energy of this state is 0, again this is 0, here again this is 0, this is epsilon, this is 2 epsilon, this is epsilon again, and this is 2 epsilon, and this is 3 epsilon, 3 epsilon, not 3, 2 epsilon, 2 epsilon, 2 epsilon, 4 epsilon, and then 3 epsilon. So, value of q we get is, so partition function q is 3 plus 2 e to the minus beta epsilon plus 3 e to the minus 2 beta epsilon plus e to the minus 3 beta epsilon plus e to the minus 4 beta epsilon. So, once you get Q, we can calculate average energy, that is minus del ln Q by del beta at constant volume, and if we do it, we get the value epsilon by Q times e to the minus beta epsilon times 2 plus 6 e to the minus beta epsilon plus 3 e to the minus 2 beta epsilon plus 4 e to the minus 3 beta epsilon. So, this is the value of average energy when the particles follow Bose statistics. And the third case, when particles obey Boltzmann statistics. In Boltzmann statistics, particles are distinguishable. So, when particles obey Boltzmann statistics. So, here particles are distinguishable as mentioned in the problem, as well as there is no restriction in number of particles in a given state. Okay. So, in that case we can work out like before and we get 16 possible distributions. And we get the partition function Q is 4 plus 4 e to the minus beta epsilon plus 5 e to the minus twice beta epsilon plus 2 e to the minus 3 beta epsilon plus e to the minus 4 beta epsilon. And from there we get average energy, epsilon average is minus del ln Q by del beta at constant volume, and then if we do it we get twice epsilon by Q e to the minus beta epsilon times 2 plus 5 e to the minus beta epsilon plus 3 e to the minus twice beta epsilon plus 2 e to the minus 3 beta epsilon. Okay. Okay, so this is the problem. And the problem part B we already discussed in the class, discussed in the lecture. Okay. So this was discussed. Now we will discuss one important thing and then we conclude this course. The one is ergodic hypothesis. It states that the time average equals the ensemble average. The average we have calculated, average quantities we have calculated so far, those are ensemble average. So, ergodic hypothesis says that the time average equals the ensemble average. Okay. So, that is a ensemble equals to a time, where A is any macroscopic variable. And how we know how to calculate, how one can calculate ensemble average, but time average we have not discussed. So how do we calculate time average? So time average A equals to limit tau goes to infinity 1 by tau t equals to 0 to tau at dt. Okay. So the basic idea is that if one allows the system to evolve in time indefinitely, that system will eventually pass through all possible states. So the ergodic hypothesis says that the ensemble average or the time average equals the ensemble average. So we know how one can calculate, or how we have calculated ensemble average so far. So we know how to calculate ensemble average, but what is time average? Time average can be calculated like a average time equals to limit tau goes to infinity 1 by tau t equals to 0 to tau at dt. So the basic idea here is that, or in the hypothesis is that, if one allows the system to evolve in time indefinitely, that system will eventually pass through all possible states. Thank you.